It's funny. Translating a language is rarely just about swapping one word for another.
Oh, definitely not.
Like if you translate a poem literally word for word, you usually just destroy the rhythm.
Right, you lose the whole soul of it.
Exactly. And translating software logic between two very different programming languages is the exact same
It
way.
really is.
Welcome to today's deep dive. We are looking at a really brilliant 2026 presentation from a developer going by the handle Look036. It's titled Python versus C++, a tale of two type systems.
Yeah, and this presentation, it's so good because it shows how translating a single tiny algorithm from C++ into Python just completely broke down.
And what's wild is that it wasn't because the math was wrong. It was because those two languages possess wildly different underlying philosophies about, how the universe works.
Yeah, it's a fascinating study of constraints because even if you don't write a single line of code in your daily life, this is really a deep dive into how the tools we build end up shaping the way we're even allowed to solve problems.
Right.
It's essentially a detective story where a stubborn little bug on a screen ultimately reveals these deep structural truths about design intent.
Okay, let's unpack this. Because every good detective story starts with a crime scene.
Absolutely.
In this case, the developer was trying to port an algorithm called a negative cycle finder from C++ into Python. And before we get into the actual code, we should probably ground ourselves in what that actually means for you listening.
Yeah, a bit of context helps.
So, in graph theory, a graph is just a collection of points nodes connected by lines, which are called edges.
Right, like a map.
Exactly, like a map. And those edges have weights or costs. So, if you think about currency exchange, maybe you trade US dollars for euros, then euros for yen, and then yen back to dollars.
That's a great real world example.
A negative cycle in that scenario would mean you loop through those trades and somehow end up with more money than you started with.
Right, it's an arbitrage opportunity. The path has a negative cost, meaning you actually gain from the loop.
Yeah, so it's a very valuable thing to find.
It is. And the algorithm's entire job is to traverse these complex webs of data and find those specific, profitable, or critical loops. So the mathematical logic is quite complex, but it's mathematically sound.
Right, and the original C++ version runs it beautifully.
Flawlessly. Yeah.
But when the developer brings this exact logic into Python, a tool called MyPy suddenly throws a massive roadblock.
Ah, MyPy.
Yeah. For you listening, MyPy is a static type checker in Python. It's like an incredibly pedantic proofreader. It scans the code before it runs to ensure all the data types like text, whole numbers, or decimals are being used
That's
correctly.
very strict.
Super strict. And this proofreader started screaming about a specific function called getWeight. The function was returning a decimal number, a float,
Right.
but the surrounding algorithm explicitly expected a whole number, an integer.
Mm-hmm.
And there was a second error doing the exact same thing at testratio.py line 47.
Yeah, so the types were fundamentally colliding. The code was trying to shove a square peg into a round hole, and the Python type checker was just refusing to let it pass.
Now, if I were in this developer's shoes, staring at this error, maybe it's 2 a.m., I just want my code to run. My first instinct would be to just slap an ignore comment on that line.
Oh, of course. The classic hashtag type ignore.
Right. Basically just putting a piece of black tape over the check engine light on my dashboard. Did they consider that?
They absolutely thought about it, along with a few other quick and dirty patches.
Like what?
Well, they considered aggressively using a cast function, which is essentially grabbing a hammer and forcing the decimal to be recognized as an integer regardless of the consequences.
Yikes.
Yeah. They also looked at just altering the input values themselves to be floats or just chopping off the decimal point entirely right where the function was called in the code.
I mean, those all sound incredibly tempting. Just bypass the alarm and move on.
They are tempting, but they're also incredibly risky. And what's fascinating here is why they rejected those band-aids. They relied on a crucial guiding principle for software translation. You always consult the reference design.
Oh, okay. So the C++ code?
Exactly. Because there was a sibling C++ implementation of this exact algorithm, that code wasn't just a previous version, it was the ultimate source of truth. Before patching the Python code with tape, they had to understand what the C++ code was actually doing with those numbers.
And since the C++ code was happily processing these negative cycles without a single complaint, the obvious question is, well, why was Python having such an existential crisis over it?
Right, which brings us to the core conflict.
Yeah, it comes down to how these two languages handle something called generics or templates. This is basically how developers write flexible code that can accept different types of data without having to like rewrite the whole program for every single type.
It's a huge time saver,
Exactly. And the Python port was relying on a feature called typefar.
which implements what we call constrained generics.
Right, constrained. And if I understand the source material correctly, typefar is super rigid. In this specific setup, Python was forcing the input values, the disk values, and the getWaitReturn value to share the exact same domain type. It was a locked-in relationship.
Yes.
If the input was an integer, the rules dictated that the output had to be an integer.
Yeah.
Absolutely no mixing allowed.
None. But over in C++ land, they use unconstrained templates
Total different vibe.
completely. The parameters for the different functions, like mapping and callable, they are completely independent. Plus, C++ has this feature called auto deduction where it just looks at the data and figures out the best way to handle the types on the fly.
It just figures it out.
Yeah, it doesn't force a relationship where none needs to exist.
It's like imagine Python has a strict formal dress code where your shoes and your belt must be cut from the exact same piece of leather. It's
Oh.
a shared constraint.
Okay, I like this.
But C++ is wearing whatever gets the job done. It treats the shoes and the belt as totally independent variables and just makes the outfit work implicitly.
The shoe and belt analogy is good, but imagine if the Python dress code also mandated that your socks had to perfectly match your watch strap.
Oh, wow.
Yeah, that's the level of artificial strictness we were talking about here. Python's typefar was actively creating a constraint that simply did not exist in the original algorithmic logic.
Because the math of finding a negative cycle does not care if the input and output types match perfectly.
Exactly. But Python's type system was halting the entire operation because of this stylistic rule it imposed on itself.
So how do you resolve that? Like, how do you make Python's famously strict type system behave a little more like C++ laid back flexible templates without just, breaking the entire rulebook?
Well, the presentation shows the developer diving into a library called digraphics and fixing the issue by using the any type.
No, wait a minute. I have to push back on this.
Go for it.
Isn't using any in Python type hinting widely considered giving up? I thought applying any literally just turns off the safety checks for that piece of data.
It is often criticized exactly for that reason. A lot of developers view it as throwing your hands up in defeat when the type checker gets too annoying.
Right.
But you have to look at the architectural context here. In this specific scenario, using any wasn't a hack at all. It was an incredibly precise, elegant translation of the C++ design intent.
I'm intrigued. How does turning off a check translate to a better design?
Because C++ unconstrained templates inherently operate by saying, I do not care what type this is up front, just pass it through and I will evaluate it independently.
I see.
By applying the any type to those specific variables in Python, the developer was explicitly communicating to the Python type checker, these types are independent, stop trying to force them to match.
It wasn't about avoiding rules. It was about rewriting Python's rulebook to correctly mirror the philosophical freedom of the C++ original.
Exactly. And they methodically applied this fix across 5 separate core methods in the code, like relax, is negative, Howard, and so on.
That reframes it completely. It's like telling the bouncer at the door, hey, this guy's on the special list, let him wear whatever shoes he wants.
That's a perfect way to put it.
But the types were really only half the battle because they still had that actual mathematical issue.
Yeah.
A decimal was being generated where a whole number was needed. C++ is very forgiving under the hood.
It'll just implicitly truncate a decimal down to a whole number, like turning a 4.9 into a 4 automatically behind the scenes.
Right, but Python refuses to do that implicitly. It forces you to be deliberate.
Exactly. Python's philosophy is explicit is better than implicit, so the developer had to manually add a truncation function, literally wrapping the cost variable in an int command. So Python knew, without a shadow of a doubt, to chop off that decimal.
And then, and this is my favorite part there, was the collateral damage to the tests.
Oh, the tests.
This part of the presentation is just, I can practically feel the developer's migraine radiating through the screen. Because of Python's strictness, the automated tests were failing over literal syntax.
It's so frustrating.
The tests defined dictionaries that expected flow values, decimals. But the actual test data inputted a literal 0, just the digit 0.
Right.
Python looked at that 0, declared it an integer, and threw a massive error because it wasn't a point 0.
It is exactly the kind of debugging nightmare that makes you question your career choices.
Seriously. Imagine having 149 tests fail because you wrote a 0 instead of a 0.0.
Painful.
The developer had to go through and fix the test literals. So a typed float dictionary actually used 0.0, but the payoff was immense.
It really was.
After making these structural and explicit changes, they ran the suite. 149 tests, 0 failures. 0 might be type checking errors.
Beautiful.
And the most amazing part, 0 changes were needed in the core Nate Toptum source code of the algorithm itself. All the fixes happened in the surrounding digraphics library and the test files.
Which is the hallmark of a true architectural victory. They solved the problem at the boundary, preserving the integrity of the core logic.
But here's where it gets really interesting.
Oh, we're not done.
Not even close. Fixing that initial type error was just peeling back the first layer of the onion. Getting the types to align pulled back the curtain on an even deeper, more fundamental divergence between how these two languages operate.
Right, it wasn't just about how they categorize numbers anymore.
No, it was about how they literally visualize relationships in data.
We're talking about how they handle complex data containers, specifically in the context of graph structures.
That's right. And this brings us to the concept of parallel edges.
This is a fun one.
Earlier, we talked about a graph being like a map of nodes and edges. Imagine a graph mapping out airline flights. Usually you have one flight path from city A to city B, but what if you have 3 different flights from city A to city B departing on the exact same day?
Okay, yeah.
Those are parallel edges, multiple distinct connections existing between the exact same 2 points.
And this is where the container type dictates reality. The C++ code was built to accept any iterable container of containers. If you visualize it, it's like a master list that contains smaller lists inside it.
Okay, so it's very flexible.
Super flexible. A simple list does not care if you add duplicate items to it. You can write milk on your grocery list 3 times and the paper won't spontaneously combust.
True.
Because of that, the C++ architecture naturally allowed for duplicate entries, which meant it effortlessly handled those parallel edges. It could map multiple flights between the same cities without breaking a sweat.
But the Python code was operating under a totally different set of constraints.
Yeah.
The original static type annotations in the Python port required something called a mapping protocol.
Yes.
And in plain English, that demanded an inner dictionary. And dictionaries in programming have a very hard rule. They require unique keys.
Which is a huge difference.
Yeah. You cannot have 2 different definitions for the exact same word in a dictionary. Because of that structural demand, Python was silently restricted to only allowing 1 edge per target node. It literally lacked the capacity to comprehend multiple flights between the same 2 cities.
If you fed it a second flight, it would just quietly overwrite the first one.
Which leads to one of the most brilliant, albeit frustrating, revelations in this entire saga. The developer looked at the Python code and realized it actually possessed a test specifically designed for this scenario.
Right, I remember this.
It was literally titled Test Multiple Legitimate Nodes.
Yes, but it was a complete illusion.
Exactly. The test was providing a massive false sense of security. Because the underlying library Python was using, NetworkX, has a default behavior of replacing parallel edges.
So that test wasn't actually testing multiple connections at all.
No, it was just testing a last right wins scenario. It was feeding the dictionary multiple edges, and the dictionary was just ruthlessly overriding them, keeping only the final entry. The test passed because it didn't crash, not because it actually preserved the data.
It perfectly highlights the danger of a test that passes for the wrong reason. It's a huge irony, too, because Python is legendary for flexible duck typing at runtime.
Yeah.
Yet its static mapping annotations made it vastly more restrictive and brittle than the C++ templates.
So, to resolve this fundamental mismatch, the developer had to shift Python's approach from nominal typing to structural typing.
This is the genius part of the fix.
Okay, let's break that down. Nominal versus structural typing. Let me see if I can synthesize this for you listening. If I understand the concept right, nominal typing is like a bouncer at an exclusive club holding a clipboard. He is checking to see if your specific name, your exact title, is on the VIP list.
That's a great visual.
In Python's case, it was demanding a container specifically named as a mapping dictionary. If you weren't named mapping, you weren't getting in.
Right.
Structural typing is a totally different bouncer. This bouncer doesn't care what your name is. He just checks if you are wearing the right dress shoes to get in.
Exactly.
He cares about your structure, your behavior, regardless of your official title. Is that an accurate way to look at it?
That is spot on. Nominal cares about the label on the box. Structural cares about what the box can actually do. The developer needed Python to stop demanding a dictionary by name and start accepting any container that behaved correctly.
And how do they do that?
To achieve this, they built a helper function called viewItems And this mechanically solved the problem by dynamically checking for behavior. Instead of enforcing a strict dictionary type, this helper function looks at the data container being passed to it and essentially asks, do you have an dot items method? Can I extract data from you in pairs?
Oh, I see.
If it is a dictionary, great, it extracts the items. But if it's a list of lists, which we know can hold parallel edges, it says, okay, you don't have an items method, but I can still iterate through you pair by pair.
It adapts based on the structure it encounters.
Precisely. And in doing so, it brilliantly mirrors a powerful C++ trick called compile time dispatch, or if Contextspr.
What does that do?
That's a feature where the C++ compiler literally looks at the data structure being handed to it during compilation and says, oh, you're a list. I'll grab the list instruction manual. You're a dictionary. I'll use the dictionary instructions. It routes the logic based on the shape of the data.
And the Python helper function replicated that exact philosophy.
Yes. It shifted the whole paradigm.
It's an incredibly elegant workaround. By shifting to structural typing, checking for the behavior instead of the name, the developer just busted the doors wide open.
Python was no longer shackled to dictionaries.
Right. They were able to add 4 brand new, robust tests to the suite tests that genuinely covered lists of lists with parallel edges, tests that hunted down negative cycles using those parallel edges, all while ensuring backward compatibility with the old dictionary formats.
Python could finally see the multi-edge graphs that C++ had been looking at all along.
It is a phenomenal journey. From a single type-checking error on a screen to fundamentally altering how a language interacts with its own data structures.
Yeah, absolutely.
So as we bring this all together, let's look at the core lessons we can extract from this 2026 presentation. Because it's not just about Python and C++A, it's really about systems thinking.
Well, the first major takeaway is that you cannot assume parity between generic features. A template in C++ is simply not the same creature as a typevar in Python.
Right, one defaults to unconstrained freedom, the other defaults to rigid constraint. When you are porting logic, you have to translate the intent, not just the syntax.
Which leads right into the second realization. When you have two different systems running the same complex algorithm and they need to coexist or communicate, you have to establish a ground truth.
And in this case, the unconstrained C++ design was the reference point. You have to mold the stricter system to match the flexible one, not the other way around.
Exactly. And that leads to the validation of our controversial any type. Sometimes deliberately decoupling types with any isn't a lazy hack. It is the architecturally correct method to explicitly tell a rigid system to behave with the necessary flexibility.
Yeah, that really changed my perspective on any. And finally, we saw the triumph of structural typing over nominal typing for data containers. Focusing on what a container can actually do, like yielding items, creates vastly more resilient and adaptable software than obsessing over what a container is officially named.
If we connect this to the bigger picture, the ultimate takeaway here is that type systems do a lot more than just catch typos. They encode a developer's design intent.
Yeah, they really do.
C++ essentially broadcasts the philosophy, I trust the operations to handle the data, so I won't micromanage the types. While Python initially broadcasted, these components must be identical for me to feel safe. When translating logic, the real work is reconciling those two worldviews.
It really makes you look at the digital tools you use every single day in a completely different light. They aren't just neutral calculators, they are opinionated systems.
Highly opinionated.
But before we sign off, I want to leave you with one final unresolved puzzle drawn directly from the What's Still Missing slide in the developer's notes at the end of the presentation.
Oh, this part is fascinating.
They did incredible work. They fixed the type system, they conquered the parallel edges, but when they zoomed out and compared the full API surface of both language implementations side by side, there were still glaring gaps.
Significant ones.
Entire complex functions like methods for extracting node pairs, find the cycle, relax node pairs, and specialized cycle finding loops were present in C++, but completely absent from the Python Next Cycle Finder port.
It raises a rather profound question about the limits of translation.
It really does. It leaves you to wonder, when you are translating deeply complex logic between two tools that hold vastly different underlying philosophies about how the world works, is true one-to-one parity ever actually achievable?
Or are we destined to always have these translation gaps?
Exactly. Where one system can express a thought that the other simply cannot comprehend. Just something for you to ponder next time you're jumping between tools. Try and make one system speak the language of another. Thanks for joining us on this deep dive.